So, good morning. Second day on directional coupled mode theory and directional coupler. And the first real building block, the first real device for our circuit. Any questions concerning the yesterday full immersion in coupled mode theory? Everything clear after the discussion you had done. Okay, we have seen that sometimes it's possible and very convenient to instead of consider a structure or device itself, consider as two separate, easier, simpler device structure, in some way coupled or perturbed or interacting. If you well remember from electrotechnics, when you studied transformer, the coupled inductor, you do not study the transformer itself, but this is just a two inductor, two solenoid, in some way coupled through a magnetic flux that combine the two. So, in several cases, in several fields, these techniques apply. So yesterday we have seen the directional coupler. We found the eigenvalue, eigenvector, so the phase constant, the shape of the mode of the directional coupler, starting from the modes of the waveguide taken separate. And we concluded the lesson yesterday with the expression of the power along the waveguides, the power in the waveguides, not in the modes. So you have the two waveguides here. This is the direction of propagation, direction of propagation, and we have seen that this structure supported two modes. That is the even mode or symmetric mode, and an asymmetric mode. If you combine these two, you get something like this, that seems the fundamental mode of the upper waveguide, or something like this, that is the fundamental mode of the lower waveguide. So sometimes it's better to think as this condition, and the two modes are coupled. Sometimes it's better to think as the real modes of the waveguide. We did some calculation, and at the end, we wrote, I wrote again, you don't need it, that the power, so we call A the amplitude of the field in this waveguide, and B the amplitude of the wave in this waveguide. So basically, A is this one, and B is this one. And we found this expression in case you start with A of 0 equal to 1, B of 0 equal to 0. And we found this expression, I wrote again. This is the power, so the square modulus. I think it's correct. Let me see. Check. Yes, correct. So this is clearly 1 minus the other one, because the power is conserved. And this is the most general case. So we assume the two waveguides are different. So delta beta is the difference of the phase constant of the two waveguides, and C square is the product of the two coupling coefficient that we obtained yesterday with the coupled mode theory. So we arrived here yesterday. Okay, and we obtained this as a combination of the eigenvector, starting with this condition. So in zeta equal to 0, so in the origin we have A0 equal to 1. In effect, the sin square goes to 0, we have 1, and the other one is 0. So this is 0, and beta is B is 0. Okay? So everything is consistent. So basically we enter from here, no from this waveguide, but after a while we have power both on this waveguide and in this waveguide. So if you think to this picture, you enter only with this mode, you don't enter with this one is 0, but propagating you have some coupling of power with a sin square law from one mode to the other one. If you think to this picture, what does it mean 1 and 0? It means that you have the symmetric mode with amplitude 1/2 and the I wrote in the opposite sign this morning, don't know why. Let me reverse this one so it's easier. Like this, and 1/2 on this. So 1/2 plus 1/2 give you 1 here, and here gives 0. So basically enter from here with the mode of this waveguide means that you excite both modes of the structure with the same amplitude and same phase at the beginning. It's clear? Okay. I draw it again here. So if you enter from here with this mode, you can think of this shape of the field like the combination of these two modes, right? It's exactly the same. Correct? Now these two modes propagate with their speed, beta s, beta a, along the waveguide. They do not exchange power, and it's clear that while they propagate, the phase accumulated is different because it's and so it is clear that at some point, the shape of the field is a combination of these two with their phase, so it's no more this one, it's something else. So in general, you have power in both. At some point, you get a 0 and 1. So it seems that the power moved from the upper waveguide to the lower waveguide. And this occurs where this is half power. So when you have this term equal to half pi, this is called bit length, the bit length of the two modes. The bit length of the two modes and the two symmetrical and asymmetrical modes are in a different phase here, opposite phase, and they combine in this way. So their sum is in this waveguide, so B is maximum and A is minimum. And then they come back again, no? Oh, God. Any doubt on this picture? It's clear? This is the conclusion of or the discussion of yesterday, basically. So if you have some question on this, I don't know, let me know because we. Yes.
Just to be sure, so we are saying that in the whole structure we have at least two modes propagating that due to their different speed they interact and create the shapes.
This is correct. If you say that instead the two modes of the two waveguide are coupled and there is a coupling of power from one to the other one, is not correct formally, but we know what there is behind, so it's correct.
So in this case, that is changing of the waveguide is the real case.
So changing?
Because you have the power that you want to from one waveguide then to the other. We have made equivalent that the real case.
You can think in both ways. You can describe the behavior in terms of the proper mode of the structure or with the coupled mode. This is the coupled mode theory on which I insisted yesterday, and is correct as well. So you can see both.
Excuse me, Prof. If we in directional coupler, so if we want to divide the say light into arms, let's say, so we control it with the length of the.
Yes, this is the directional coupler. At the moment, I'm still on the coupled mode theory, and now I move to the directional coupler. So just a second, and I will arrive. Sorry to insist a lot on this because it's a powerful technique and is important. So now we start with the directional coupler. So.
When we were seeing last week about the simulations, we could see the mode structure.
Sorry, when?
Last week when we were able to see the simulations, those simulations will we be able to see this structure?
You see the total field.
That is the
You see the total field, so this one.
not this we can't see.
Well, you can see if you launch only one mode. If you launch only this one, you see this one that propagate, that continue, and is always the same. Does not change shape and amplitude. Continue. It's a mode. And also this one. Because you see the intensity, you don't see the phase.
After the coupling, the beta will be
After the coupling,
so something like beta S and beta symmetric and symmetric divided by 2. Just beta here in the sun. It's just beta, not beta odd or beta even. In the phase
this is beta of the symmetric mode, beta of the antisymmetric mode,
after
and this mode has a beta 1 and this other mode is beta 2. The difference is delta beta. The sum does never appear, just in the formula of the beta S and beta. The average beta.
average beta.
Yeah. The average beta. So we get this result from the eigenvector, with this assumption: 1 as A0, 0 as B0. So basically, this refers to this situation. So we enter only from the top. Okay? Now, assuming you have to solve another problem. For example, you enter from the bottom and not from the top. And then you have to solve another problem. Enter from here with an amplitude 0.37 and here with an amplitude 0.5. Well, every time you have to combine the eigenvalue, the eigenvector, find the solution, etc. No? So it would be better to have a unique formula for every situation. So we consider now this one. a very compact description of the behavior. So this is our directional coupler. We have a wave on this side and we have a wave on the other side. And we want something that describe the link between the complex, because of complex amplitude field, the complex amplitude at the output is a function of the complex output in the input. Complex amplitude at the input. And this is a matrix, transmission matrix of the directional coupler. It's a 4x4 matrix with 4 elements. And you can write that use the same, so I use the same. Use the same symbol. No. Which they are. I don't know. A0, B0, and this is A at the distance zeta, and this is B zeta, and we can write A zeta, B zeta, the vector of the two amplitude of the output as a function of the amplitude at the input, so A0 and B0. So if we can write this matrix, then we have solved any kind of problem. Every input can be in some way transferred to the output. And this is the general solution.
The matrix TC is called what?
Transmission matrix of the directional coupler. So this element TC11 is the amplitude of the output, A zeta, is the contribution to the output, the upper output, of the input, the upper input. So it's basically this term. This is the amplitude of the output, this output, the lower output, and you can write as a function of the input. So, in the previous example, this term, TC21, is what is this coefficient link the upper input to the lower output. So it is exactly this one. So this term is this one, and this term is this one. Now if you do the exercise another time, you can, for example, enter from the bottom and so find the other two coefficients here. It's not difficult to understand that the matrix is symmetric, so it's easy to fill. And at that point, you have the output for every kind of directional coupler, for every kind of input. So it's a very powerful way to describe the behavior, the circuit behavior of your device. You see now the electromagnetic approaches disappeared. Everything is summarized, hidden inside this coefficient. And it's very simple to use.
Can you explain again TC11?
Now we write the entire matrix in a more general, a more simple form, and not so complex.
How you obtain it from the so it's linked is an input and the output of the second is the
This expression is the output B, okay, when you enter from the top with a unit amplitude field. So this is exactly this coefficient. While the upper one, this expression is exactly this coefficient. So now we can write the matrix and I can fill the entire matrix. And I write in a more general case and then we simplify the word. So the transmission matrix of the coupler is this one. There is a phase term in the front that is not very important. And then let's write in this way. Where delta is the square root, as we already found, and don't write on your note, everything is written here. R is delta beta divided by 2 delta, S is C over delta, and I think that's all. Delta beta is already defined, C is already defined, and we have this relation because the power is conserved, and that's all.
Yes.
Okay. Sorry. So this has been obtained from this term. You recognize this is the power. So we have the square, but so S is exactly this term, you see, and then there is a sin of the square root, so delta, zeta, delta, zeta. So this is very easy to recognize. This one is a little bit more complex, but you see this matrix is very simple, very symmetric, very straightforward. And this permits to calculate the output of a coupler, whatever it is the input. So with this, we basically solved any problem. So if we now want to write the amplitude or power along the waveguide, we have just to take the right coefficient. If you want the power, you do the square. If you want the phase is inside. So this is really a complete and rigorous description of the coupler. Rigorous in terms of coupled mode theory. So if the two waveguides are very, very close, even touching, well, the coupled mode theory is a little bit approximated, and also this one is approximated. But in general, the two waveguides are not so close, so it's an excellent description of our direction. We see that there is a periodic transfer, and the periodicity is delta. So the power is transferred from the upper waveguide to the lower waveguide and back with a periodic behavior, and the period is given by delta. So when we have delta zeta equal to half pi, all the power went down because it's a sin, so you move from 0 to 1. And this length is called the coupling length. So we can write here LC. And so the coupling length, over which you have the transfer of the power, is delta divided by 2, pi divided by 2 delta. So pi divided by 2 square root delta beta to the square plus c squared. And then after another LC, it goes up again.
The whole period is 2C. The whole period is 2 LC. The whole
The
one.
entire period is 2LC, yes. But usually we are interested to couple something, so we define LC instead of the period. I wrote this, I put an arrow from the upper waveguide to the lower waveguide. As all the power goes down, only a part. Not all the power. So if you remember the expression before it, I can write now, the power is the square of this. So S to the square sin square, where is S is this one. So this expression, this is the power in the lower waveguide. So the maximum of power that we can transfer is this one.